So far in this course, we've learned about descriptive statistics like the median and the quartiles and the spread of the data, and then we developed theoretical tools to learn about inference, things like the confidence intervals and hypothesis tests and so on. This week we're going to consider linear regression, or lines of best fit, or how to understand linear relationships between the data. We already saw a little bit about this way back when we looked at the scatter plots to understand in a first way the relationship between two quantitative variables. Now we're going to get into it in more detail. So to start us off, let's go back to one of our favorite examples, the skeletons. And you may recall that we looked at a graph before, a scatter plot of the age difference between the estimated age minus the actual age at time of death of the skeletons, as compared to the BMI, the body mass index of the skeletons, to see if there was some relationship. Now, if we just drew a scatter plot, it looked kind of like this. It was a big jumble of dots. But then we talked about various ways of understanding it, things like the correlation and so on. And one of them was a line of best fit through the data, which looks like this. And we said, well, from this line of best fit, we can understand certain things, like, for example, the slope of the line, which in this case is positive and is about 0.41, which means there's a slight positive relationship. It means when the BMI gets larger, then the age difference seems to get slightly larger on average. But then you might wonder, first of all, how did we come up with this line of best fit, and what are its properties and so on? So to start us off, let's introduce a bit of vocabulary. So we have the dependent variable, or response variable, which is, we'll usually call it yi's, and it's the values that we're interested in trying to predict, in this case like the age difference between the estimated minus the actual age of the skeletons. We also have the independent variables, also sometimes called the explanatory variable or the predictor variable, and that's what we'll usually call the x's, and that's in this case like the BMI, and we're seeing to what extent the BMI can help us to predict the values of the age difference. So this line that we're going to come up with, well, you might think of a line as having a formula like y equals mx plus b, and that's what we're going to do. It's more common to use slightly different letters and call it y equals b0 plus b1x. So we have a line like that, and we're trying to come up with the values of b0 and b1, which are the best they can be to make this line describe the data as well as possible. So how do we do that? Well, we can think that at a given point xi, the line value would give us a value for y, which is equal to b0 plus b1 times xi. But the observed value for y is the yi. And the difference between these two values, or the residual, is just yi minus b0 minus b1 times xi. We'd like to make these differences be as small as possible. Well, we don't just want them to be small because then they could go negative. So we might want to take their absolute values, or it turns out to be easier, kind of like we did for variance and so on, to take their squares. So we'll look at actually the sum of the squares of all of these differences between the observed values of y and the values that we would get if we plugged in xi into the formula for the line. And this gives us a big sum of squares, as it's called, and then we want to find the values of b0 and b1 which minimize it, which make this sum of squares as small as possible. Well, this is a job for calculus. So if you remember your calculus, you'll remember that we want to find a critical value, so we want to make the partial derivatives of this sum of squares with respect to b0 or with respect to b1 equal to 0. Now that's kind of a messy problem, but you can work it out, and you end up with these crazy formulas here for a formula for the value of b0 and a formula for the value of b1. Now in this course, we're not going to try to work these out by hand. We'll usually let the computer do it for us. But it's important to understand that there is a formula and there's no judgment involved. We're not eyeballing what seems like a good line of best fit. We're using a formula to find the line of best fit which minimizes this sum of squares of the differences between the predicted values and the observed values. In this example, when we work out those whole formulas, or let the computer do it for us, we compute that b0, which is sometimes called the intercept, works out to minus 23.3 years. And B1, which is sometimes called the slope, works out to plus 0.41. And that's what gives us this red line that we've graphed here. So how can we interpret these values? Well, 0.41 as a slope is saying that when the BMI increases by 1, then this age difference increases by 0.41. So it's a measure of how much the age difference increases when the BMI increases. Similarly, if the BMI were to decrease by 1, then the age difference would decrease by 0.41. So that explains the slope. What about this intercept value, B0? Well, one way to think about it is that's the value that the line would give us if the independent variable, in this case BMI, were equal to 0. Now, in this case, the BMI can never be 0, so it's not really that useful to interpret this intercept value, or a B0, in terms of the value when BMI equals 0. So we just think of it as how much we have to shift the line in order to get the line of best fit. Here's another question about slopes. Suppose we were to graph it the other way around. That is, instead of trying to do a regression of the age difference as a function of the BMI, suppose we try to do a regression for the BMI as a function of the age difference. Well, since we're just swapping things around, you might expect that the slope would just get swapped around to be the reciprocal, to be 1 over the other value. Well, let's try it and see. Here's a linear regression where now the independent variable, or x value, is the age difference, and the dependent variable, or y, is now the BMI. Well, in that case, we get a graph like this, and we can see that we again have a red line with a slightly positive slope. But is this slope just 1 over the other slope? No, not at all. This slope is equal to about plus 0.046, which isn't even close to 1 over 0.41, which was the other slope. So, in other words, regression is not symmetric. Regressing one variable against another is not the same as regressing the second variable against the first one. For one final example, let's remember a graph that we saw earlier, a scatter plot for the countries and territories of the world, comparing their life expectancy in years compared to their GDP per capita. Well, we can see from this graph that the countries, as you might expect, with the higher GDPs also tend to have higher life expectancies. And indeed, we can fit a line of best fit, or a linear regression in this case too, and that red line gives us some sense of the relationship. It has a positive slope, in this case equal to about 0.45 years for every $1,000 of GDP per capita that the country has more. And the intercept in this case is 63.3, and that's again hard to interpret because it's sort of saying if the GDP were 0, then the life expectancy would still be 63.3 years, and that doesn't seem quite right, and indeed some of the data seems to contradict that too. So this suggests that there's more to the story than just the linear relationship, and indeed we can see that the points on the graph here seem to have their own behavior, which isn't just linear. So we'll come back to this point later of how to understand relationship in ways other than just the linear fit or the linear regression. Anyway, in all of these examples, we see that one possibility when comparing one quantitative variable to another is to take a linear regression where one of the variables is the independent variable and then the other variable is the dependent variable, and we use a line of best fit or linear regression which has a precise formula that you can work out on the computer to give us exactly what is this line that does the best job of trying to fit the data in the sense of minimizing the sum of the squares of how far the line is from the corresponding point. And in this case, we get a formula. In the lectures ahead, we'll learn more about how to interpret this formula and how to interpret this line and what it all means.